Good morning.
Good morning.
Okay. I think we technically covered all the material Friday. And I want to review, make sure I didn't miss anything, go over alternate versions of notes, start answering questions, that kind of thing. So more interactive than straightforward lecture. That's my belief. Does that sound right? Well, at least it doesn't sound wrong. Okay. You see one assignment is up, and I believe people are already submitting or working on those things. And there's another assignment similar to it that will be opening up Sunday night, and then it's due Monday. So you 24 hours to get that completed. And I think I've got 3 of those throughout the semester or something like that. Most of these are more open-ended, like the one you already see. I muted you, William. I think you can unmute that, though. Ah. All right, let me share my screen then. And I've got a couple things to talk about there, but mostly I wanted to start here. Let me run through these notes again real quick and make sure that I didn't miss anything. Or if you have, if it reminds you that you had a question about something, that's fine. We didn't talk about EB and F enough, I don't think, but it's pretty straightforward. Hopefully we all know what a language is now. Is that a fair statement? We know
yes, sir.
We know what grammars are, and we're starting to work with examples. So then the question starts to become, how comfortable are you working with the grammars? How comfortable are you creating them? And obviously, normally the way you get better at things like that is practice, practice, practice. Right? So I think these notes are pretty well done. We did regular expressions on Friday, did we or didn't we? Did we stop at Chomsky?
Yeah, I think we stopped on the Chomsky hierarchy.
Okay, so we do need to finish regular. One of my problems is, I've done the pre-recorded version of this, so I never know if I'm talking to myself or talking to you guys when I'm, I remember having gone through the material. All right, so let's do regular expressions. If you took CS332 with me, you've seen this before. I think if you took it with Jaiwei Young, I don't think he covered it. But if you took it with myself or with, who's the woman from the math department that does a really good job? Anyway, I believe she covered it also. Okay. When we go back to the Chomsky hierarchy, the type 3 languages are called regular. And as we said, there's very strict forms of the BNF grammars on those. Left-hand side contains exactly 1 non-terminal. Number of terminals on the right-hand side cannot decrease. And strings can be derived either from left to right or right to left. Those are regular grammars, and they correspond to the regular languages. And it turns out regular languages can be expressed in a form called a regular expression. And it's just a shorthand way and a more formal way to do the definitions. What we'll find in the next week is that each of these languages, each of these types in the Chomsky hierarchy have a corresponding model of computation, and the model of computation that corresponds to regular languages is the finite state machine. So we'll worry about that next week. But that's where we're headed with this, is for each one of the languages in the Chomsky hierarchy, we'll talk about what kind of model of computation that corresponds to and why we care. Okay, regular expressions, informally defined. I'm going to say RE is the set of regular expressions, or RE is equivalent, an equivalent usage of that is RE is the set of languages that can be expressed by regular expressions. In other words, regular languages. Lambda, the empty string, is a regular expression. And any single symbol in the alphabet is a regular expression. If I have U and V that are also already regular expressions, then their concatenation is a regular expression. If I wanted, concatenation is a one-time operation. If I wanted to keep concatenating, I could keep concatenating the same thing over and over again. For example, instead of doing U and V, I could take U and U, a copy of U, and concatenate it one time. Well, if I can do it one time, why can't I do it more times? So we can get repetition. If U is a regular expression, then 0 or more copies of U is also a regular expression. And the reason I say 0 or more is because that would give us lambda, which we've already agreed is in the regular expression. That's written as U star, and the star is known as the clean star, because that's the person who first decided to use that symbol and got the name attached to it. We can also do copies of 1 or more. So the clean star is 0 or more copies. Sometimes it's useful to require at least one of something, so you can do 1 or more. And instead of a star, you use a plus sign, a superscripted plus sign. And then the OR operator, it's technically an exclusive OR operator, also works. If U and V are in regular expressions, then U or V are in regular expression, or as a regular expression also. So that's the OR operator. We call it the OR operator. It's technically exclusive OR. What happens is when you encounter this in your regular expression, U or V, you pick one of them, exactly one of them. You can't pick both of them. Now, if this thing has a star next to it, then it's saying you can do this 0 or more times, so you can keep doing it over and over and over again. So you could pick U one time and V the next time, and U the next time, and V the next time, on and on. But on any single choice, you can pick exactly one. So technically, it's an exclusive OR operator. How does that work with examples? Lambda, the empty string is regular. We'll prove all this next week. Any single symbol in sigma in the alphabet is irregular. So the alphabet is composed of A and B. A is a regular expression, and so is B. If you think about it from the grammar standpoint, ask yourself, could you create a grammar if the language only contained the single string A? That's it. Could you create a grammar for that? I think the grammar for that would look like start string A. Right? That's the only rule I need. That make sense? And then ask yourself, does this meet the rules for a regular grammar? What are the rules for a regular grammar? Does it have a single non-terminal on the left-hand side of every rule? Yes. Do the number of terminals on the right-hand side never decrease? Yes. Did you create the string from left to right? Trivially true. Trivially yes. So that's a regular grammar. So we can accept these things as truths, or we can actually work through why they're true. If u and v are regular expressions, then uv is regular expression, and the example here is if I have a, b, b, a, which we think would be regular, and b, 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 a, b, 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 a, b, which are regular, so is this. Right. All you're doing is concatenating them together. If you can concatenate them one time, you can do it as much as you want. That's the clean star notation. So A star means 0 or more copies of A. If you need to do a grouping like this, A, B, B, and in parentheses with the clean star means that that group A, B, B can be copied over and over. So you can do larger patterns. The variation on the clean star is the superscripted plus operator, means 1 or more. By the way, A plus, which means 1 or more, is also equal to A star, isn't it? Isn't that the same thing as A plus? It's 1A followed by 0 or more copies of A. And the A plus is 1 or more copies.
That makes sense.
Right? Now, whoever came up with putting the superscripted plus operator wasn't clever enough to attach their name to it. So, you know, it's not like the Bob Smith plus sign or anything like that. You know, clean star has a name. This is just the superscripted plus sign. And then we get the or operator. So this means you get to choose A or B, not both. And as I said before, if you need multiple copies, you put the star or the plus sign, superscripted plus sign outside of there, and it means 0 or more copies of that internal expression. But what's the internal expression? The internal expression says you pick an A or a B every time you make a copy. So you can choose an A one time, a B the next, a B the next, and A the next. With what that means is, if you wanted to create any sequence of A's and B's with no rules, that's how you say that. By the way, sigma star is what we were saying earlier was shorthand for all possible strings made from a language, made from an alphabet. And now that hopefully will make sense to you. It's basically you're just smacking the clean star onto the alphabet. Okay, here's the formal version. Good old recursively defined sets, the way we learned it in CS332. For a recursively defined set, you always need to have some kind of a base case, and then you need a recursive rule where you create new elements based on the old elements or the elements that already exist inside the set. So here's my base cases. There's lambda is a base. Oh, this is an image, so I can't mess around with it too much. Let's see what I can do here. Those are my base cases, lambda, and any single element of the alphabet. And then everything else is a recursively defined definition. So everything else depends on things that are already in the set. Concatenation, clean star, superscripted plus, and the or operator. All of those require that the things that you're working with are already in the set. So that's why it's a recursive definition. Okay. Some examples. Uh-oh, is my audio messing up? It's been doing this on my recordings and I don't know why.
It's a little wonky, but I can still get like the gist of it.
Got a speaker pickup, I think, down here. And I think when I put my hand down here to type, I sometimes cover it up, but I'm not sure. what we need to do is I need to try to figure out troubleshooting to make it happen so that I know what the problem is. But this is probably not the best time to do that, right? Yeah, okay. So it just keeps going up and down and up and down. All right. I'm going to keep my hands away from the keyboard as much as I can. We'll see if that makes it more stable. Like I said, I don't know what the problem is. So maybe it's I don't know, self-modulating or something. Okay. All right, let me see if I can figure that out over time. Okay, so sigma star is all possible strings. That's a boring language. Anytime you have everything included or nothing included, it's boring, because you always want to have systems that have some kind of a distinction. You have some numbers are in, some numbers are out, or some answers are yes and some answers are no. Anytime all the answers are yes, that's a boring system. Anytime all the answers are no, it's a boring system. Okay, then I may label these things L1, L2, and so on, so we can talk about, you know, G1, G2. All strings having one or more A. There's an example for you. And there's exactly one A in here that is required right there. Once I get my 1A, I don't care anymore what happens to the string. I've already met the requirement for the string, right? It has to have at least 1A. So once I get the A, I don't care what happens, and that's why I have the A or B star after that. Because that's what we said was a good way to say anything. A or B star is a good way to say any possible string. I do have to figure out, or I do have to take into account that that 1A may be preceded by any number of B's, 0 or more B's, and therefore I have the B star in front of it. So that's how do you construct these regular expressions? You construct them by thinking about the language, thinking about the smallest string that is in the language, and then thinking about how you might make that string grow. How does it get added to on the front or on the back? And sometimes you have to come up with different, like different categories of strings almost, because they might meet different conditions. And then again, you start out with the smallest string in that category, build out that category, and keep going. For example, if I had a language, remind me to come back to this one. The language has to have at least 3 B's in a row or at least 3 A's in a row. Doesn't have to have both. It's an or operator. See, now I've got categories of strings, right? Because the shortest string is either BB or AAA. And then I could figure out how to grow those things.
Professor Garfield, in that case, could we have, would we have like 2 start symbols?
No.
Like it could be either that or?
No, but your start symbol would immediately give you, based on that first rule, you could immediately get it off from there, but you still would start with one start symbol.
Okay.
And then you would immediately say, okay, I'm either going to have strings that meet the AAA criteria or strings that meet the criteria. And you can do that through the production rules. That sounds like we should come back to that. Okay, so these are examples of the regular expressions. And then I think I turned some of these into grammars at some point. No, I didn't yet. Okay, so let's do that. Let's see, if we wanted to do let's do that in real time. That was the one we were talking about a minute ago, right? So let's see. First, can we do the regular expression for that?
Question really quick.
Sure.
Is that L4 supposed to say strings that have at least a sequence of is 3 A's or 3 B's at least one time in them?
Yes.
Okay, just making sure.
Yeah. I'm typing fast in real time, so I'm gonna screw it up. So what we can have is that. Right, that meets the criteria. And then we can say, yeah, but anything can come before that.
Wouldn't you need to have the superscript plus sign at the on the middle term, sequence of A's and sequence of B's, since it needs to appear at least once?
No, because the superscripted plus sign means one or more, but I just need it once. So if it's there, it means one.
Oh, okay.
Right. The fact that I have 3 A's means that's going to
all right.
one time. The plus sign means it could be one or more.
More.
The criteria is just one. And then if we try to make a grammar for that, shockingly enough, Canvas really does a better job of this. Okay, so the grammar could be something like S goes to, let's see, how am I going to make these strings? I'm going to make these strings from the middle out. I'm going to say this. S goes to A, or A, B, 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 A, and then A goes to A,
Sir?
or B, A, or lambda.
Professor, wouldn't you have to build it left to right or right to left for it to be regular language? And since it's
Yeah.
a regular expression, it needs to be regular language.
Right, so this is a good question. If I wanted to build a regular grammar, then I would have to build it from left to right or left to right, or right to left. That's correct. That's correct. So if I made a regular grammar, then it would have to be built from a left to right or right to left. Now this grammar, first of all, let me make sure I'm clear what I'm doing. I'm using this shorthand where I use these vertical bars to put rules on the same line. So rather than have S goes to as 2 separate rules on separate lines, I'm just shortening this. So this grammar, the way I was writing it the other day, looks like this. And one of the shortenings that you do with the extended Backus-Naur form is, that starts to get long and ugly, is to try to make it a little less ugly. So I'm doing it this way. This means that you get to choose between the rule that you want. So before I answer the question that Adam had, does that make sense to everybody, or is there a confusion going on there?
The grammar makes sense to me.
Okay, so that grammar makes sense. Now, that grammar is not regular, but we believe that the language is regular. Are those two true statements? Number one, the grammar that I have is not regular. The language is regular. Those are both true. Is that correct?
I believe so. I believe so, yeah.
Yeah, I would too. Those are good statements, right? Now, how can that be? How can I have a regular language, but I don't have a regular grammar? Is there something wrong with that, or something screwy going on?
I don't think it's necessarily screwy because you said we can have the highest tier type is the highest language it can go, but if the type, it can go any below that. So like 3 is regular, 2 is
Okay.
2 is context free in that, so it could be any of the ones below regular as well.
Right. In fact, that grammar is context free. Here's the rule for a regular language, and I believe it's in the notes this way. It better be in the notes this way. You have to be able to construct at least one grammar that is regular. That doesn't mean every grammar that you construct is regular. But for that language, you have to construct at least one grammar that is regular. Then you know it's a regular language. We can create a regular grammar by doing it this way. I'm going to do S goes to A. A goes to A, or, whoops, gosh, I'll get there, B, A, or A, B, or B, 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 and then B goes to AB, or BB, or lambda. Do you see what I'm doing? I'm saying S goes to A, and then I can make any possible any number of A's and B's in any sequence that I want, just by keep going, using those two rules over and over and over again. At some point, though, I have to get either an AAA or a BBB, so I never let this non-terminal A disappear. I never let it go to lambda or just terminate. Instead, it gives me that AAA, or it gives me the BBB, and then in both cases, it moves on to the second half of the string. And the second half of the string just keeps making A's and B's for as long as I want. And when I'm getting tired of it, I just quit with lambda. But that grammar is the same as G4. It produces the same set of strings, but it is regular because it meets all the rules for regular. So since we have created at least one regular grammar for L4, we can confidently claim that L4 is regular. Thoughts?
So you have either A or B at the beginning, then you have to have either 3 A's or 3 B's.
Right.
And then A or B at the end, potentially. But
Right.
in these grammars, wouldn't it be possible to write a string that doesn't have 3 A's or 3 B's? Because the A could go to either AA, BA, or you know what I'm saying? Like, can you write a non-valid string?
And that's exactly the right question that you have to ask yourself when you're writing these, or when you're checking mine. You have to ask, okay, first of all, does it create all the strings that are in the language? And then second, you ask, and this is sometimes the harder question, does it create strings that are not in the language? And that's the question I think you're asking, right? Is are we guaranteed that every string will either have AAA in it or BBB in it? That's the question, right?
Yeah, like, is that okay to have
Well,
in that
well,
grammar?
that's, you tell me. Can you construct a string using that second grammar that I have? Can you construct a string that does not have an AAA or does not have a BBB? And that's the right question. I'm not trying to put you on the spot or criticize you. That's the correct question to ask.
So because you have AAA and then B, and the only way to actually end it is to have B, and because that
Right.
could be lambda, so
Right.
that, okay.
Right. If you think of it as going through a maze, you are in the land of capital A, right? You're in the capital A room. And the only way to get out of the capital A room, because if you go through door lower A, you end up back in the capital A room. And if you go through the lower door marked lower, you go back in the capital A room. The only way to get out of the capital A room is to get into the capital B room. And you can only do that by using door marked AAA or door marked BBB. I don't know if that's a good analogy or a bad analogy, but it's kind
No,
of,
that makes sense.
you're going through the maze, right? And you can't get out of the A's. You can't stop with capital A's or get rid of it from your string until you get at least a triple A or a triple B. Then you're stuck with these capital B's, but that's a lot easier problem to handle because capital B will eventually, you can just choose to go to lambda. And that's the right way to think of these things. You know, you ask yourself, like I said, does this make every string that's in the language? And then does it accidentally make strings that are not in the language? And we'll find the same question crops up when we start making finite state machines next week. Does this machine match the language?
I got a question for you.
Please.
So is this basically the only, there's other ways to do this, correct? Could you have like capital B, AAA, capital B,
Oh,
and that would be
so,
correct?
yeah. So how many grammars can I make for language 4? How many correct grammars can I make for language 4?
You can make as many as you can, right?
That can make an infinite number, right? Right. So to answer your question, yes, there are multiple correct ways to do this.
Okay.
Yeah. Which is always fun to grade these things, right? Sometimes students will come up with shockingly elegant solutions, and it takes me, half an hour to convince myself there's no way that simple grammar can make all those strings, and it does. And then sometimes students make shockingly inelegant solutions, and I have to go through all the different paths to make sure that the strings are there. Okay, so that's, let's see. In addition to these notes and the recorded lectures and these lectures, in addition to those things, I did give you, and tell me if I didn't, because I'm sure I did, these kinds of notes where I have the actual PDF version of the notes, which are much more verbose. Formal definitions, discussions, examples, right? These notes are on your let's go to these guys, these notes, example problems, practice problems in PDF form. That covers, I think, remember that the PowerPoint slides never contain all the information. So if if you think there's holes in the information or you can't remember what I was saying in a particular lecture, then you can look at this, which is a fuller definition. It has all the same information, but it may be better to use as a reference, more precise. I think, Matthew, what I'm going to do, I don't think we're going to need 3 lectures this week. So I'm going to use the lecture sessions as office hours this week. And that may be how every week goes. We'll see how much effort the lecture sessions are. Okay, so we have those. And then I have some example problems, and these are worked out. So if you don't like the way I worked them, then ask questions. If you see an error or you think you see an error, ask questions. So these are provided for you as worked out problems. And I'm using the extended Backus-Naur form here where I'm using the vertical lines as, to shorten things. So this is grammar G3. Rule 1 is from the start symbol, but then rule 2 is A goes to AA, and rule 3 is capital A goes to capital B. That's the way to read that. And when I'm asking you in your assignments to derive strings, I'm asking you to do this kind of a format where you say, this is the rule that I used. So if you have questions about any of these, we can go over them. I think, by the way, going back to what we were just talking about, here's let's see, G5 is context free. I'm just reading this from here, and I'm trusting that I was right when I wrote that. But then I created an unrestricted language for G5 by adding a trivial rule where I made some of the terminals go away, which is part of the unrestricted part. Right? The unrestricted part says you can make terminals go away. So again, this just goes to show you, you can create an infinite number of grammars for every language, most of which are stupid and useless in that they have some kind of a useless rule. But that was the point, that the way you can classify the language in terms of the grammar is how high up the Titan can you go, right? I think Adam was saying it that way. If you can make a single regular grammar for a language, that language is regular. If you can make a context-free grammar for a language but not a regular one, then the language itself is context-free. So anyway, there's some examples worked out for you. And then here's the thing that I think you really will get benefit from. I just gave you a whole boatload of different languages to try to create grammars for practice. And then same trick, right? So here's another language, write a grammar for it, and then answer questions about it. And these are the exact same questions that I believe I'm putting on the assignment. By the way, the palindrome language, number 3 here, and the properly nested parentheses, number 5 there, are classics. Those show up in every single textbook. And the reason that they're classics is they start to draw the line between the regular languages and the context-free languages. It turns out that, we don't need to worry about this till the end of next week. It turns out the canonical non-regular language is one where the number of A's and the number of B's are equal to each other. And we'll see why next week. It's basically the reason is you have to keep track of how many A's and B's you have. And you can't do that if you're building a string from left to right, because once you start building from left to right and you're moving on the string, you don't know how many A's you built to make sure that you have the matching number of B's by the time the string is done. So that's why those are there. The palindrome language and the properly nested parentheses language. By the way, if you can do properly nested parentheses, you can also do simple mathematical expressions, right? Just by filling in. Think about how you do math expressions and how you show precedence through the parentheses. So that's what that's about. So by all means, Wednesday, it would be great if all I have is questions about this stuff from you guys. That'd be great. And then what else did I want to show? Last thing I wanted to show you. These grammars are theoretical in nature. They do bound computation, but they have a highly practical use. I don't know if anyone's done this yet, but here's the Java syntax specification in BNF form. So literally, the parsers and the compilers use the Backus-Naur formats to define the language. And the thing to worry about, the thing to look at here, and this goes back into extended Backus-Naur form and how we're going to use this stuff. Here's the same thing for C. You can use all of this stuff. Look at what kind of types do you have in C? Type specifier. It can either be void, char, short, int, long, float, double. Sound familiar? So what happens when you're they use these brackets to mean non-terminals, and then these things that actually show up as keywords in the language are the terminals. You can take a simple C statement and actually start here at the top, find the start symbol and work your way down to the expression that you have or the statement that you have. It's actually easier to go backwards, and actually that's what compilers do. So for example, if you're doing a declaration and you say that something is a double, then the first step in compilation is to go through your program and do what's called lexing, and they'll take that double and they'll replace it with just, oh, that's a type specifier. That's all that is. So your program, if you think about it, you have all these different variable names, but as the program is being parsed, the first thing that happens is the lexer goes through and says, what's the job of this particular string? That looks like a variable name. I'm just going to call that a variable name, or whatever they use for the non-terminal for that. And then from there, they keep parsing your program. Here's your assignment operators. They're all the forms of the assignment operators. So again, you can go through and see how this works with real world languages. And when we talk about the section of compilation, about midway through the course, I'll bring this up again. Java is a little tougher, a little larger of a specification, and the deal is here is all these class. First you get into classes, and then you get into attribute and variable declaration and method definition. So it's a little bit larger, but I think I forget. I counted this one time. It's 150 lines or something like that. But they get right down into digits. So they can do new constants. You can't do constants without digits, right? All right. I just wanted to show you that. I also found this. I don't know what this is yet, but it looks like if you make your own Backus-Naur form, this thing might be able to start creating a converter for you, or a compiler. There are standard compiler builders out there. Yeah. Okay, that was just kind of a quick side trip. Are there other questions before we go? Did I put you all to sleep?
No, I'm still up.
Yeah,
I'm good.
You're like me, you never woke up yet. Just still that coffee, yeah. Okay, all right, then I'll see you Wednesday, but what I suspect we'll do Wednesday is just, I'm gonna open it up to questions, and then Friday, we probably don't need to meet at all, but I'll reserve this for office hours. That's the way I think this will go this week. All right?
Yes, sir.
Wonderful. See you on Wednesday then.
All right. Thank you, Professor.
Thank you. Bye.